Hi, Hola, Bonjour, Salaam. Welcome to Blueprint Bazaar. Today we are advancing our simulation journey by tackling Problem 2, the integration of human factors. While machines and pallets follow rigid mathematical distributions, real-world manufacturing relies heavily on human operators. In this session, we aren't just modeling a workflow, we are modeling human nature, specifically how fatigue and recovery cycles impact production efficiency. We will be building a digital twin of a workstation powered by a source, but with a critical twist. The traitor, or treatment process, is now dependent on a worker who moves, tires out, and requires recovery time. To build the foundation of this system in Simio, we start by placing our core objects. We add a source named Source 1, a server for the workstation, and a sink for the finished products. However, to represent the human element, we add a worker entity and two basic nodes. One node acts as the stop node, or the resting area, and the other is the work node, located directly in front of the workstation. To connect these, we create a walk process using a path or time path that allows our operator to move between these 2 points. This physical movement is vital because it adds a realistic delay. Work cannot begin until the operator physically arrives at the station. The logic of our operator is governed by 2 key variables. First, we create a Boolean state variable named worker@station to track whether the operator is in position. Second, we define a positive integer variable called WIP, work in progress. To make this dynamic, we go into the state assignments of the workstation to update the WIP value every time a part enters or exits the queue. This allows us to create a worker behavior process. When WIP is greater than 0, the operator is triggered to move from the stop node to the work node to start processing. Conversely, when your WIP equals 0, indicating there is no work to be done, the operator returns to the stop node to conserve energy. The most sophisticated part of this problem is the fatigue index, Fi. We define a state variable for worker fatigue that increases during active work and decreases during rest. To solve the mathematical requirements provided, we must calculate the fatigue rate such that 6 hours of continuous work leads to a 99% fatigue index, and a 2-hour stoppage results in a nearly total recovery of 1%. By integrating this index into the operator's behavior, we move away from ideal cycle times and toward realistic production forecasts. To visualize this in Blueprint Bazaar, we add an animated graph to the model, allowing us to watch the fatigue curve rise and fall in real time as the simulation executes. To truly bring this human element to life in Simio, we must implement the logic of fatigue accumulation and dissipation through specific processes. The fatigue index doesn't just sit there. It is a dynamic state variable that we update continuously or at discrete events. During the traitor, or treatment phase, we use a process to increment the fatigue index based on the calculated rate where 6 hours of labor hits that 99% mark. This means as the simulation progresses, the worker's efficiency could be linked to this index, perhaps slowing down the service time at the workstation as they become more exhausted. This creates a realistic feedback loop, where the throughput of Source 1 is directly limited by the physical stamina of our human operator. The recovery phase is just as vital for a sustainable manufacturing system. When the WIP reaches 0 and the worker behavior process triggers the operator to return to the stop node, we switch the logic from fatigue accumulation to recovery. Based on our requirements, a 2-hour stoppage must lead to a quasi-total recovery of 1%. This recovery logic is modeled in Simio by decreasing the fatigue state variable over time whenever the worker is at the stop node. By watching the animated graph, you can see the sawtooth pattern of the worker's energy levels. This visualization helps us identify if our current workload is too intense. If the fatigue index never has a chance to drop back down to near zero, we know the operator is headed for burnout, which would eventually halt the entire production line. To calculate the specific rates for this model, we apply a differential approach to the fatigue index. For the accumulation phase, we determine the rate such that the index reaches 0.99 after 6 hours of continuous work. Mathematically, this involves setting up a rate of change that mirrors physical exertion. Conversely, the recovery rate is calibrated so that a 2-hour work stoppage, where the worker is stationary at the stop node, brings that index back down to a 0.01 level. Beyond the fatigue calculations, the movement logic adds a critical layer of spatial realism. Because we have defined two specific basic nodes, the stop node for rest and the work node for the station, the worker must physically traverse the path between them. This means the system is waiting for the human element twice, once for the physical travel time and again for the actual processing time at the server. By setting the worker at station Boolean variable, we ensure that the workstation logic is locked until the operator is in the correct coordinate space. This prevents the teleportation of labor that often occurs in simpler, less accurate models, giving us a true look at the workstation's actual capacity. The ultimate goal of this Problem 2 simulation is to determine the average stock level and the peak fatigue reached during a 4-hour window, representing half a working day. When we analyze the results, we are looking for the maximum value of our fatigue state variable to see if it hits a dangerous threshold. If the average stock, or WIP, begins to climb indefinitely, it indicates that the human-machine system is unbalanced. Either the arrivals from source 1 are too frequent, or the operator's recovery periods are insufficient to maintain the necessary pace. These insights allow us to redesign the workflow, perhaps by adjusting the processing speed or adding a second operator, ensuring a sustainable and efficient production environment. To accurately model the complex interactions between human endurance and industrial output, we must establish a precise set of state variables within the Definitions tab. These variables act as the system's memory, allowing the simulation to track changes in real time. The first step is to define the WIP, work in progress, as an integer state variable. This is crucial for our control logic. It increments when a part enters the workstation queue and decrements when it leaves. By monitoring this integer, the worker knows exactly how many units are waiting and can decide whether to stay at the station or head to the rest area when the value hits 0. Next, we establish the core of our human factor analysis by creating the fatigue variable, which must be set as a real state variable. Unlike the discrete steps of the part count, fatigue is a continuous value that fluctuates based on exertion and rest. To govern how this fatigue level moves, we define two more real state variables, mu and lambda. These represent our recovery and accumulation rates, respectively. We calibrate lambda so that 6 hours of continuous work pushes the fatigue index to 0.99, and we set mu so that a 2-hour stoppage allows the index to drop back down to a quasi-total recovery of 0.01. We also need a way to track the worker's physical location within the model's logic, so we create worker at station as a Boolean state variable. This is a simple true/false flag. When the worker is in front of the workstation, the value is true, allowing the server to process the work. When the worker is at the stop node for recovery, the value is false, and the process remains idle. By integrating these 5 variables, WIP, fatigue, mu, lambda, and worker at station, we create a sophisticated digital twin that respects both the laws of production and the limits of human physiology. By monitoring these variables through an animated graph, we can observe the direct correlation between the accumulation of WIP and the rising fatigue index. If lambda is too high, or the worker doesn't have enough time to recover via the MU rate, we will see the fatigue hit its maximum threshold, signaling an unsustainable workflow. This level of detail ensures that our engineering recommendations are grounded in realistic, data-driven principles. These calculations allow us to solve for the average stock levels and peak fatigue during the required 4-hour work window. Once the logic is running, we evaluate the system over half a working day to capture the maximum fatigue index achieved. This analysis reveals the hidden impact of human factors on workstation performance, such as the idle time created when an operator must recover. By comparing the results of this model with and without the operator, we can identify how much stock accumulates in the WIP during rest periods. This final data points us toward the most efficient and ergonomic design for the manufacturing station, ensuring that production targets are met without overextending the human workforce. Beyond the immediate production metrics, this simulation provides critical data for workforce management and ergonomic design. By analyzing the time in state for the worker at station variable alongside the fatigue real state variable, we can determine the exact efficiency loss attributed to human exhaustion. This allows engineers to test what-if scenarios, such as decreasing the arrival rate from source 1 or introducing a scheduled break, to see if it lowers the maximum fatigue index without significantly increasing the average stock levels. This proactive approach to simulation helps in designing a system that is productive while prioritizing the long-term health and performance of the operator. The integration of these specific state variables also paves the way for more advanced modeling, such as linking the server's processing time to the current fatigue value. As the fatigue variable climbs towards 0.99, we could use an expression to proportionally increase the service time, mirroring the real-world slowdown of a tired worker. This creates a highly accurate nonlinear model where the system's capacity is not a fixed number but a fluctuating value dependent on the history of the work performed. Capturing these nuances is what transforms a basic, discrete event model into a high-fidelity digital twin that truly reflects the complexities of modern manufacturing environments. By mastering these state-based behaviors and fatigue calculations, you can build simulation models that are not just mathematically accurate, but human-centric and practically applicable to real-world facility management. This advanced exploration of simulation logic demonstrates how the interaction between state variables like WIP, fatigue, and worker at station creates a high-fidelity digital twin that respects both the laws of production and the limits of human physiology. By analyzing these dynamic relationships, engineers can move beyond rigid, machine-only models to design manufacturing environments that are truly sustainable, balancing high-performance targets with the realistic endurance and recovery needs of the human workforce. This is Blueprint Bazaar. Keep building, keep simulating, and we'll catch you in the next deep dive. Please keep supporting us as we dive deeper into mechanical design and development. Don't forget to like, share, and subscribe so you never miss a step on this engineering journey with Blueprint Bazaar.